let's now look at an example of solving a problem with that Arrhenius equation that we just looked at. I want to look at an example reaction that actually does use the SN2 type mechanism that we were looking at as a possibility earlier on in the semester. So this reaction is going to involve pyridine, this molecule. It's a 6-membered ring with nitrogen in it and some double bonded carbon. It looks a little bit like benzene. However, it has a nitrogen with a lone pair that you might recall looks like it can behave as a nucleophile. This is going to react with methyl iodide. That's CH3 bonded to iodine. Very much as in the case we looked at with T-butyl chloride, this iodine is going to be able to leave that molecule. So these are our reactants. And once the reaction is complete, the structure that forms will be this one, with nitrogen now bonded to the methyl group. This makes a positively charged molecule that can be paired with the resulting iodide. This, by the way, is actually drawn to energetic scale. That is, in this case, iodine with a negative charge is more stable than pyridine on its own. So if this is an SN2 reaction, one of those reactions that involves going through a central transition state, that transition state would look like this. The carbon center has become flat because simultaneously the bond with the iodine is breaking and the bond with pyridine is forming. So this is our transition state structure. And it's observed that relative to the reactant here, this transition state has an energy of 58 kilojoules per mole. So the question is, what would our reaction rate constant be? To determine that, we do actually need one more piece of information, because the Arrhenius equation that we want to use is this one. We have our activation energy. We're going to be determining our KT at room temperature. That's K for Kelvin up there. So we know our temperature. We know our R because we can look that up in a table. In particular, it's 8.314 times 10 to the negative 3 kilojoules per mole Kelvin. You do want to be careful with R that you choose the version with the correct units that are going to be useful for what you're working with. In this case, you can't take an exponential of something with units, so we need everything up here to have its units cancel out. That's going to work out okay because our activation energy is being divided by R, which will cancel out kilojoules and cancel out moles, and the temperature will cancel out the kelvins in there. So the last thing we need to know is a value for A, for our frequency factor. And in this case, it's equal to 3.2 times 10 to the 6th per molar seconds. So that frequency factor is telling us about the shapes of these molecules and how they collide with one another. That's information that would need to come either from experiment, that is, you would run this at one temperature and then use the Arrhenius equation to figure out the value at another temperature, or from relatively advanced theoretical calculations. So, with all of this information available, let's plug it in and see what it gives us for a reaction rate constant. Another quick thing to probably mention as we're writing this out, recall that our reaction rate law is going to have a rate that depends on moles per second or some pressure unit change like bar or Pascal per second. So we're relying on our rate constant to multiply times our individual concentrations or other components in the rate law to give us the right units. One of the very weird things that means is that A, our frequency factor, is responsible for giving the rate law constant the right units. That's part of why we're getting this rather odd per molar seconds as a unit for A. We're going to multiply that times e to the negative 58 kilojoules per mole divided by 8.314 times 10 to the negative 3 kilojoules per mole Kelvin times 298 Kelvin. Now is a great time to make sure that you feel comfortable doing these kinds of exponentiation operations with your calculator. The result is that at 298 K, we get a value of 2.6 times 10 to the negative 5 per molar seconds. This is going in one direction. It should be apparent that it's also equally possible to run this math in reverse, to use an experimentally determined rate constant to figure out an activation energy.